Okay, guys, so let's begin our next topic. We're going to be starting equilibrium today. Equilibrium is something that is going to be a little bit new to you. Up till this point, we have mostly discussed chemical reactions in terms of a single direction. For example, A gets converted into B, and all of A is converted into B, and there's no A left. Unfortunately, that is oftentimes not the case. We don't have these reactions that proceed in a single direction. Oftentimes they can proceed in both directions, the forward and the reverse direction. And so we indicate that with this little double arrow that I have drawn there. And so an example reaction generic might be reactant A plus B produces product AB, but the converse reaction is also true. The chemical AB could turn into A plus B. It could decompose to form A plus B. So this reaction is what we call a reversible reaction or a two-way reaction. And you'll find that many reactions are reversible or two-way. And so you might ask yourself, how can that be? I thought we only went one direction. Well, let's look at an enthalpy level diagram for a second, and it might help you to understand that. So if we have this enthalpy level diagram, to go from the reactants to the products, we have to overcome the activation energy, and then we'll proceed in that direction. There is nothing at all preventing this from going in the opposite direction. All we have to do is overcome the activation energy in the reverse direction. And so it certainly can proceed in both directions as long as we overcome the activation energy that is required to produce the reverse reaction that is possible. So equilibrium, the correct term we're actually going to use here is dynamic equilibrium. So we might want to add that to the front there, dynamic equilibrium, because at equilibrium everything does not stop. We just have a cessation of overall, the net change of reactant to products is not going to change anymore, but there are still things occurring at the atomic level. The reaction is still proceeding forward. It's also proceeding at the reverse direction. It happens to be that at dynamic equilibrium, those rates are the same. And so let's look at, let's try to piece this thing down into the atomic level. So got a beaker here. It's got atoms A and B in it, a whole bunch of those atoms. And initially, as this reaction begins to proceed, there's no AB. There's none of the AB molecule. And so we might have a plot like we've been looking at in the past topic where we have, we're plotting concentration of A, concentration of AB, and concentration of B. We are initially going to have a bunch of A and a bunch of B, and we're going to have no C. So let's make B blue. So we're going to have A and B, and as A and B begin to react with each other, their concentrations will begin to decrease. And they're probably going to be along the same line since we have a one-to-one reaction in this hypothetical. As the concentrations of A and B decrease, AB is being produced. So we're producing in here some A and B while A and B are combining to form AB. Now at some point in this reaction, because there is less A and less B as we're consuming those, the rate of the reaction is going to slow down. And so we're going to produce less and less AB as there's less and less A and B available to react. And as AB is produced, and there's less and less A and B producing AB, we're going to stop producing AB. And so the reaction is going to level out. And we would describe this reaction at this point of leveling out, we would describe it in the terms of dynamic equilibrium. It is in a state of equilibrium, meaning that the concentrations at this point, the concentration of A, the concentration of B, and the concentration of AB are now unchanging. their concentrations are stable. They have equilibrated with each other. And so that would be a state of dynamic equilibrium. Now, at the microscopic level, at the atomic level, there is still an A molecule can still collide with a B molecule to produce an AB molecule. But what's happening at the atomic level is that every time one of those occurs, it's occurring at the same rate as an AB molecule splitting back into an A plus B. So the net change is equal to 0. There is no more net change in the concentrations at dynamic equilibrium. And so that's kind of your basic equilibrium concept. It's not overly difficult to understand, but some people have a little bit of difficulty with it. Let's talk about some characteristics at dynamic equilibrium, and that will be it for today. All right, so characteristics at equilibrium. So some things that you just need to kind of know, and it helps you understand these. So the first characteristic at equilibrium is that the forward rate is equal to the reverse rate. The rate of the forward reaction and the rate of the reverse reaction are the same. And so that's why the concentrations stay the same. The concentration of the reactants and the concentration of the products are unchanging. They don't change. That's where the equilibrium comes from. So the concentrations are unchanging. The concentration of the reactants and the concentration of the products may be equal to each other. They may not be equal to each other. That is dependent upon the equilibrium expression. And so they don't have to be equal to each other. Equilibrium does not mean that the concentration of the reactants and the concentration of the products are equal to each other. So don't make that mistake of misinterpreting the equilibrium word there. It's possible that they are equal to each other, but they don't have to be. And they're more than likely they're not going to be equal to each other. The odds of them being equal are very, very low. So they're most likely not going to be equal to each other. At equilibrium, there is no observable change. There's no observable change or no macroscopic change. I already mentioned that there are atomic level changes. There are atomic changes. A is still reacting with B in the reaction. It just happens to be that the rate of A going to B is the same as the rate of AB turning back into A plus B. And so there's no macroscopic change, but there are atomic level changes.